Good afternoon, everyone, and welcome to Dan Goldin's masterclass. I encourage everybody that is sitting in the back to come please up front, because you're in for a treat of a deep dive on how to make the impossible possible. If you were part of the keynotes this morning, you got a glimpse for it. And so please don't be shy. This will be worth your while. And without further delay, Dan, the floor is yours, sir.
Earlier today, I talked about a number of very specific activities and programs that I had the privilege of initiating or fixing up and working with the amazing, amazing team at NASA. These people are just off the charts in terms of their capacity to get things done. And I'm hoping that they're going to pull off a number of really important things over the next 5 to 7 years. But today, I want to look at a number of the principles I talked about earlier today, and we're going to have a few tests, voluntary, of course, but I'd love everyone to participate. So let us begin. I'm going to talk about 5 specific programs. The International Space Station, which America worked on with 17 countries. It was quite complex getting it started, especially since I spent 25 years of my life trying to take down the Soviet Union. And then 4 or 5 months later, President Bush had me sworn in as a NASA administrator. That was George H.W. Bush in April 1st of '92. And 2 months later, I was sitting across the table at Blair House from Boris Yeltsin. It was kind of an out-of-body experience, but it's a new world, and it's absolutely wonderful. In spite of the tensions between the US and Russia, that space station is still up there, it's still operating, and it's done as a team of people from 18 countries or 16 countries, I keep forgetting the exact number. But it's a testimony when people work together and they have a common objective, they understand what they're supposed to do, the darn system works. Okay, so we have the space station. I'm going to talk about the Hubble actual rescue, not some of the technology that led up to it. Then I'm going to talk about this Pathfinder mission, which was a demonstration of clarity in terms of simplicity of requirements and allowing a team with very focused requirements the freedom to generate any way they wanted. I'll talk about the X-43A, which holds the world's record, Guinness Book of World Record, Mach 9.68 in 2003. This was done for $300 million, and there's probably tens of billions that have been spent. And then my experience with the web. So let's begin. This morning, I talked about how one manages a business and constantly keeps the business fresh. And I broke things into frogs and caterpillars. Frogs, I'll just repeat for those that haven't been there in the first lecture. I use the term frogs because if you put a frog, I guess it could be true or not true, but it's folklore. Put a frog in a pot of water, turn up the heat, the frog will keep swimming until finally it will die. And all of us have been involved in activities that really deserve to be canceled, but because of tradition, because of egos, because of a variety of other reasons, we don't kill them. And on the other end of it, I'll talk about caterpillars, which are animals that don't look very attractive when they first come out, and then they turn into beautiful butterflies. And having an ability to recognize the frogs from the butterflies is essential, especially in an engineering business. So let's talk about the frogs. The National Aerospace Plane. Here was a plane that was supposed to travel Mach 5 from San Francisco to Tokyo, and the fundamentals of leading-edge heating weren't worked, and they had hopes, wishes, and dreams when you did the computational fluid dynamics and projected what that leading edge was going to be. There wasn't the material available to do it, yet the program was proceeding on hopes, wishes, and dreams. And then, even though computational fluid dynamics wasn't where it was supposed to be, it was not where it is now, it still was good enough to be able to predict where the flow separation occurred from laminar to turbulent, and they didn't work that. As a NASA administrator, a few days into the job, I called in the team to ask them those two questions, and they couldn't answer it. They had already spent $1.6 billion, and they were planning on spending $12 billion. That was a frog. Get the picture? On the other hand, there is the X-43A. After we canceled the National Aerospace Plane, I said, okay, I want Mach 10, and I want a scramjet that is, it's an air-breathing engine, so you don't have to take liquid oxygen, you just burn hydrogen, and through a scoop you pull in the oxygen, even at higher altitudes. And instead of building a system, and we'll go into a lesson on it, instead of building a system that was steady state, they made the heat transfer system thermal inertia. So they put in a little extra weight, and they said we could get 30 seconds, and we get to Mach 10, and they got to Mach 9.68. So sometimes you have to seek simplicity instead of elegance. And when elegance comes in, we'll go through a little exercise on that one. Space commercialization. NASA, up until 1992, had not thought about the possibility that companies would provide services. And during my hearing to be approved by the Senate for the job, I said I want to dock in the skies with small spacecraft that are very inexpensive, and we'll do it faster, better, cheaper. And at the time, there was a very low density of small spacecraft. The reason I did that is putting a spacecraft at geostationary orbit takes a lot of energy. It's very expensive to get there. It's very expensive to build it. So young people and even older people couldn't start companies and start doing things instead of the government. So we started going to much smaller, low-orbiting spacecraft, and I said we're going to dock in the skies. And if you take a look, they're now worried that we'll have too many spacecraft in low Earth orbit. But there are hundreds of small companies now that are providing commercial services not related to government in low Earth orbit. Let me move on. Okay, this is question number 1. There's a method to my madness, it's okay. I have 2 containers. One container could take 9 quarts, and the other container could take 5 quarts. And I know I have a sink, and we were going to do an experiment here, and I thought it was going to get pretty wet and messy, so I didn't. But I have a sink, I have a water supply, and I know when I put the water in, it's exactly 9 quarts. The meniscus comes right to the edge. It's exactly 9 quarts. Same for the 5 quart. I could fill up each one of these things multiple times, pour it out. I'd like to have someone tell me how I could end up with 6 quarts in a 9 quart container.
So you'll be left with 1 quart in the 5-quart container and 9 quarts in the 9
Well, you have to do it twice, right?
Yeah.
So you fill it up with 5 quarts, then you you put in 4 quarts.
Yeah.
Now you have 1 quart.
And then you empty out the 9-quart container and then put in the 1 quart you have in the 5-quart container, refill the 5-quart container, and then put it.
Boom. Did you do it by visualizing the final picture and work backwards? Or did you just jump to it?
I don't know. I just tried to solve the problem.
Well, no, there's a method here. And it's something that I developed years ago. Before I do anything, I visualize what the final solution looks like. I get an image in my head. I'll talk a little bit more about that later. But I get an image in my head, I visualize the solution, and then work backwards. Try this. It really, really, really works. And in fact, I'll tell a story here about the International Space Station. I actually use this technique. I was a holdover. I was the only holdover from George H.W. Bush, who was a Republican, to the Clinton administration, which was Democratic. There may have been one other person from the FDA. So in any case, the new administration came in. They asked me to stay until they were going to replace me. And I got a call from the head of the Office of Management and Budget, a gentleman named Leon Panetta, who later became the Secretary of Defense and the CIA director. And he said, Dan, I want you to come over and see me. I went over to his office, I think it was Friday, February 8th, 4 o'clock in the afternoon. And he said, Dan, I have this problem. Bill Clinton ran on a promise that he'd eliminate the federal deficit. Every different government agency has to cut the budget. So if we cut this amount of money from you, all we have to do is cancel the shuttle, the space station, the astronaut corps, and your human spaceflight. And I said, Leon, are you out of your mind? They're going to come up with pitchforks and take out President Clinton. So I said, you want to ask me a different question? So I said, yeah. Leon, here's what I want you to ask me. I have a financial problem. I need to eliminate so many $1 billion. Dan, could you give me a solution? I said, boom. And I said, give me 2 weeks and I'll come back with a solution. And he said, no, the president needs to know this on Monday. I want you here Monday morning and I want you to tell me how you're going to save, I can't remember, $40, $50 billion. Tell me how. He called me on it. I was in a state of panic. And I went through an exercise with 7 other people. Tom Stafford, the astronaut, had a house in Old Town Alexandria, so we lived there for 48 hours. It stunk to hell by the time we got to Monday morning. But we went through this exercise, and we tried to visualize the future. Instead of nibbling it up to it, which could have taken months, we tried to visualize 3 solutions, and I didn't do this exercise on them, but we agreed we had to visualize the solution and work backwards. The president selected option B. There were 3 options, and that's exactly what we launched to space. So it really, really works, and I'll try and find some other examples. Okay, let's move on. Okay. This is something I learned from a psychologist called Miller's Rule. And what I'd like you to do, could someone time out 3 minutes when I say go? What I'd like you to do is start in the upper left-hand corner, go all the way to the right, and then if you get that far, keep going. I'm going to shut it off after 3 minutes. I'm going to ask you to replicate this chart, starting with the upper left-hand corner, going that way, that way, that way. And I want to see the crowd. You usually need about 200-300 to get it statistically correct, but we're going to learn from this exercise. Trust me, okay? Who's going to be my timer? You are? Start the clock now. Stare at this. Does everyone understand what I want? Questions? Start in the upper left-hand corner, stare at it, and then see if you could replicate this, starting in the upper left-hand corner, going to the right, going, okay? Start the clock now. Well, we have something very interesting here. Do you notice? Out at 14, there's a peak, and there's a peak at 7. This is called Miller's rule of 7 plus or minus 2. We did pretty well in showing that. The psychologist said humans can retain 7 plus or minus 2 things. Whoever did this over here probably looked at the numbers 2 at a time. when I've run this test with like 500 or 1,000 people, I found people who did 3 at a time. So it's Miller's rule of 7 plus or minus 2, and then it could be 14 plus or minus 4. But if you see, we have a distribution function here. Now, why am I saying this? When I go to due diligence on companies, and I've done hundreds of them, there's such a desire to show all the information you have. And by the way, my rule is 3 to 5. People want to show everything they know, but there isn't a comprehension. The human brain doesn't have the capacity, unless you're way out here. I guess we got someone out there, a few people. So the point being, you want to focus. The other thing that it does is you want to get rid of superfluous ideas. And I'm going to give you an example of real-time application of Miller's rule 7 plus or minus 2 on the Hubble Space Telescope. When I first became NASA administrator, CEOs of multi-billion-dollar corporations came in, and they would have 50 PowerPoint slides. And after they were on slide number 3, I would say to them, "Why are you here?" Now, this happens all the time when I'm talking to startup companies in my venture mode, and even in growth companies. People want to put so much information down that in the end you lose. And then if you take a look at attacking very difficult technical problems, you want to focus. And if you don't focus and you have too many options, your brain goes crazy. So keeping an intensity of focus, and I generally go 3 to 5. I favor 3, and I'll sometimes go to 5. I don't even feel 7's enough. But as you're going through your developments, as you're going through customer challenges, try and keep yourself highly focused. So now let me tell you the story here. I don't think we have the picture of the Hubble. But the crew, the NASA team had developed the contact lens for the Hubble. And then what happened was people violated Miller's rule of 7 plus or minus 2. I got there late, so I couldn't stop it. But what happened was I asked the crew to tell me how much time they needed to make all the changes they wanted. And they said, we need all 11 days. The shuttle only had so much fuel, so much life support, and it'd have to come back. And I said, that isn't going to happen. Because what if something goes wrong? What if you can't take a box out? What if you can't attach something? And I said, why in the hell do you have 11 things that you're trying to do? Can't you get a priority of focus? So I said, get out of here and come back. And I want to be able to, before the mission goes up, to tell the American public and the president exactly what to expect. So if you're saying you have to do 11 things and you have no reserve time, it's going to be a disaster. So the other part of this lesson is, in advance, define what success is. Don't have success define you. And many times people are coming out with a new product and they make it do too much. So instead of meeting the most important criteria, the 3 criteria, they want to show 7 things or 10 things, and when you fail on the 10th one, the whole thing's a loser. So intensity of focus, prioritize, and sure enough, they came back and they said, we only need 7 days. We don't need 11 days. So we have 4 whole days of margin, and they put it in exactly the right order, what had to be. So I had confidence to go call in the press corps, which is really, these are heavy-duty people, and you don't want to screw up with them. And I defined what success was going to look like. We had a 4-day margin, and the better news was they got 11 things done. So then there were bonus points, and taking something from a $5 billion failure to a whole success enabled the American people to support NASA again. So this really happened. Okay, let's move on. Simplicity and clarity of requirements. When you limit the number of things you're promising, you gotta make them simple. I'll give you another example of this. Let me see if we go forward here, if I don't screw it up. Whoops. I think I have screwed up. Yeah, okay. Good. So we talked about this. I'll come to this in, oh yeah, so simplicity of requirements. When I arrived at NASA, they had a spacecraft going to Mars. It cost $1 billion, and they took 10 years to get there. And they used a control system, you can't make this up, for geostationary orbit, and it was going to go into orbit about Mars. You think the control system had a problem? Yeah. And it was built and launched and failed. So NASA needed to have a recovery. So I said, I'd like the NASA team, this was in '93, I said, at the end of '92, I said, I want to fly a spacecraft to Mars. I said, land safely on Mars, deploy a robot, and do good science. The mission requirements document for the Mars orbiter had failed. Now, it was 3 things, not 7, it was 3. And I said, you have 3 years, and you have $300 million to launch. That's 1/3 the price and 1/3 the time of the failed mission. And it's 1/10. And up until that time, when America or Russia or other countries landed on other planets, they used retro rockets. You have 2 sets of rockets, and with any problem, it's conditionally unstable. And on Mars, I think there are 17 spacecraft that crashed from Russia because of retro rockets. So in making 3 things, land safely on Mars, deploy a robot, do good science. Why did I say that? Because the minute I said deploy a robot, if you have to go to a precision place, you could land anywheres, and then the robot gets to where you need to be. But the first thing is land safely. They didn't go into orbit safely about Mars. So land safely, deploy a robot so you don't get wound to retro rockets. And the last thing is do good science. Usually at NASA, do good science is the first thing. But if you don't land safely and you don't give a safety relief valve, you're not going to make it. So in any case, they came up with a spacecraft. They looked at airbags. They went to the manufacturers in Delaware, and they said, could you build a giant airbag so we could put our spacecraft inside this airbag? And when the spacecraft gets close to Mars, it'll drop it with a parachute. It'll fill the airbags. It'll cut a cord. And then the airbags would bounce 300 feet into the air because there's very little friction from the atmosphere there. It bounces, it lands, out comes a robot, and you send it to where you want to go. They did it in 3 years, not 10. They did it for 300 million, not $1 billion. Now, the first mission that went to Mars was Viking. I'm so old I worked on that. It went up in 76. And that was, in equivalent money, $3 billion, and also 10 years. So it was very simple. I'll show you a video at the end of what it feels like to do the impossible, and you'll see the excitement. Okay. Simplicity and clarity are requirements right from Miller's rule of 7 plus a 2, adopted by Goldin, the 3 to 5. Okay, next. Understanding the physics and Miller's rule again. You can't make this up. They didn't understand the physics on the National Aerospace Plane. It's pretty simple to do computational fluid dynamics. Really simple. And it's really simple to figure out what the leading edge is going to be and not spend 5 years. No, they started it in 84. This is 92. So that's 8 years. And they had the fiction that they're going to somehow invent non-obtainium that was going to do the job. So you understand the physics, and then after you understand the physics, you apply Miller's rule to narrow it down. Okay, I'll come back to the pictures, and we'll go through it. Okay, here's another problem. I have 6 sticks here. You can't stretch them, you can't bend them. I want 4 equilateral triangles, equal-sized equilateral triangles. Who's making a square and putting 2 diagonals in the square? Pythagoras' theorem, 1 the square root of 2, that ain't going to work. You'd have to stretch the rods. Okay, let me give you a clue. What if you thought in 3 dimensions? Because everyone got locked into the board when I ran my hand across these things, and you thought in 2 dimensions, and your brains are stopped. You now could work in 3 dimensions. What's the answer? Boom, a tetrahedron. It looks a little difficult, but I'm not a great artist with a computer. But all of a sudden, when you go into 3 dimensions, all of a sudden things change. So the problem is in the design, people get so locked into living in 2 dimensions and 3 dimensions, sometimes you got to go to the 3rd and the 4th and the 5th dimension, and you got to keep your mind open. So I'll come back to these principles in a minute, but I wanted to give you, and I do these silly exercises just to make a point. I'm not trying to torture anyone here. What do you think you could do with these things here? What kind of objects do you think you could make? Could you make a house? Could you make a rocket? Here's the problem. I trapped you. And I'll show you that it's pretty simple if you think about it. My colleague, Joy Shin, went to the web and used generative AI to get this stuff. But many times, people try and think of too many things before they get the question. Now, if I said, my question is, could you make a dog? Or a rocket? There's a rocket. I did that last night. Here's a house. There's a forest nearby. You need imagination. And there's a dog. So many times you have to say the question is, what is the question? It's unbelievable, and I'll tell you how we conceived the Webb Space Telescope because of this little exercise I gave you. Okay, let's move now. The space station. Visualize your endpoint and work backwards. Leon Panetta wanted a solution in 48 hours. I didn't have 3 months or 5 years. I want a solution. So I got 7 of the smartest people I ever met in my life. One of them was Max Faget, who's the man who invented the shuttle. These were people, one of them was an astronaut. These were people and we visualized the future, we worked back. It certainly didn't have that level of detail. It didn't have that level of detail, but it was right in the ballpark, and we divvied up the work. And one of the things we said is in Space Station Freedom, the Americans didn't have a skyhook. You need a place when you put up the first element to hook it on. They didn't have a skyhook, but the Russians did. They didn't have an airlock, but the Russians did. They didn't have a docking mechanism, but the Russians did. So we put that into here. They didn't have a crew rescue vehicle. If something goes wrong, you want to bring the astronauts back. The Russians had that. The Japanese had this. The French had that. The Germans had that. And just with recollections, we visualized that we wanted a system that had room for everybody. It was safe, and it was affordable. So we visualized the future, then we worked backwards, and we came up with option A, B, and C. 48 hours. The Hubble. I told you about the Hubble of Miller's rule of 7 plus or minus 2. They delivered on that, and it caused them to prioritize. When you have a limited number of things, you don't just present it out in arbitrary fashion. You prioritize what is the most important thing, the next most, and then the next most, and the next most. And all of a sudden, you could define success for a new product launch. There are three things I want to tell the world. This is the first most important, second, third. When you're going in to get VC funding or private equity funding, this is the number one thing we're going to do, number two, number three. This comes up over and over and over again. Pathfinder. Simplicity of requirements, but you want to lead the provider. I led them by giving them the flexibility of not having to land at a precision spot. I prioritized for them land safely, because this is a landing. If it's an orbiter, orbit safely, land safely, deploy a robot, do good science. The scientists have a tendency to prioritize the science, and then they go kill each other to see who's going to get the best part of the science. This time we led with engineering. Okay, the National Aerospace Plane. They prioritized. They had to meet a cost bogey, so they knew they couldn't go steady state. Because if they went steady state, they'd need a thermal system that would be much too heavy, much too expensive. It would grow up in size. It would be billions of dollars. It was their idea. I just said, here's 300 million, get to Mach 10. And they said, the only way to do it is to take advantage of thermal inertia. It's amazing how creativity comes out when you bound it and don't give people wide open sky. And then finally, the web. This was an interesting one. 2 years to the day that we fixed the Hubble Space Telescope, a delegation from the National Academy of Sciences and National Academy of Engineering. This is the highest level that engineers and scientists get. They came to see me. And I'm also a member of the Academy. But they thought I was a nose-picking NASA administrator and didn't understand science. And they came in and they said, Dan, we have a great idea. We want to launch a new telescope, and it's 4 meters in diameter. The Hubble was 2.4. And the reason they were so excited is the log of the area ratio is the increase in the signal to noise. So all of a sudden, who cares about signal to noise? And then they said, we want to launch this thing, and we want to put it into Earth orbit. I said, why do you want to do that? They said, well, everything gets launched on the shuttle. So they're thinking in one dimension. Every spacecraft that goes up goes on the shuttle. And they just didn't have their act together. And they didn't know what question they wanted to ask. So I said, what question do you want to ask? Don't tell me about how to do engineering. You're scientists. They said, well, Dan, we want to see the first stars that ignited after the Big Bang. I said, wow, that's a pretty big Doppler shift. And you're not going to see it in the visible. You're going to see it in a long wavelength IR, and that means you have to be exceptionally cold. How are you going to remain cold in Earth orbit? And then they said, well, yeah, I was leading the patient. They said, you know, in order to do that, we really don't have enough collection area. We need to be between 6.5 and 8 meters in diameter. So I said, why don't we do it? They said, it's impossible. You can't build a telescope that big. I said, why not? They said, because it's got to be a solid mirror. I said, why? And I'm repeating some of it because there are some new people here, so I apologize for repeating. So I said, why? They said, it's impossible to get a good surface finish if you do it deployable. So I said, and sometimes when I'm thinking, words come out of my mouth as though I'm in an out-of-body experience. And I took my hands like this and I said, Why can't we build a deployable adaptive mirror and put piezoelectric materials to control the surface, and then use motors to align each of the devices? They said it's impossible, cannot be done. Impossible, cannot be done. So they pre-decided the answers. So they didn't even know what question to ask. They didn't get their physics right because they wanted to go into Earth orbit, because everything, if it's a nail, it needs a hammer. Put it into Earth orbit. So after a battle with them, I sent them out of my office. I went in January to the American Astrophysical Society, AAS. I gave a 1-hour lecture on a deployable, adaptive, passively cooled, they have a radiator. Oh, the other thing, they want to go to Earth orbit. That thing is in Lagrangian 2 point, and that's the exact place, I think it's 1 million miles away, where the pull of the moon, the sun, and the Earth is okay, so you don't have to do any attitude correction. So it went to L2. And all of a sudden at L2, it's really cold. You don't have to worry about albedo radiation. So that's how these principles got applied. Thank you so much for listening to me.